Section 7.7, we're going to deal with a topic called complex numbers. It's a new type of number system that we haven't dealt with yet. It is the end of Chapter 7, which is the end of our discussion on radicals, and so we will be seeing some roots in this section, particularly square roots. We're actually going to focus quite a bit on square roots. And so we're going to start off by looking at a topic that we've talked about in the past just a little bit. We've made mention of it, but never really dove into it. And it's this idea that you cannot take a square root of a negative number. Okay, if you were to do that, you would get something. Let's just assume we could do it. Okay, we'll call it question mark. Well, if we could do that, then that's like saying, remember, square roots are undoing a square. It's the reverse of a square. So if we could do that, it would be the same as taking that thing, right, question mark, squaring it, and getting -1. These two things are equivalent to each other. Okay, so, well, that can't happen because anytime you square something, you multiply it by itself. The two factors, because it's the same thing, would have to have the same sign, and you can't multiply two things with the same sign and get a negative number. Negatives only come from multiplying a negative with a positive. And so there is no real number whose square is negative. Okay, so this question mark cannot be a real number. Not possible. Okay, the real numbers, of course, are everything between -infinity and infinity on the number line. So it cannot be in this interval. Well, that's saying a lot because every number we know so far is in that interval. So there must be some other numbers then that are in that or that are not in that interval. Okay? So this question mark must be something else. So it's not in that interval. And so if it's not in that interval and we've never seen it before, we're just going to define it as something. We're going to give it a name. The name we're going to use is an imaginary number. In fact, we're going to call it the imaginary unit. So the square root of -1 is going to be equal to, we're going to call it I. Instead of question mark, we give it a name. It's the number I, not the letter I. And it represents what we call the imaginary unit. Okay? Now, this number does not exist in the interval from -infinity to infinity. It's somewhere else. Okay? But what it does tell us is that I squared must be equal to -1. Right? So if you take the square root of -1 to get I, then the reverse is true, that this is the number whose square is -1. Simply by, you could square both sides or whatever you want to do there. Okay? So it's the only number we know so far where this can occur. So the square of I is negative. I is negative. Okay. So now let's look at other powers of I. First of all, I to the 0 power, anything to the 0 power, we'll look at 0 first. Anything to the 0 power we know to be 1. Right? That's just a common, that's our exponent rule for 0. I to the 1 power, well, anything to the 1 power is itself, so that's just I. We already looked at I squared. That's -1. And now if we look at I to the 3rd, that's kind of an interesting one, because I to the 3rd, I'll take this off to the side, could be seen as I squared times I, right? If you separate that out. Add the powers together, 2 and 1, you get 3. Well, I squared we already said is -1, so this is -1 times I, or simply -I. Okay, so that is going to be what we use, is -I for I cubed. Okay. What's also interesting is that if I were to do this again for I to the 4th and I to the 5th, we're going to find some pattern evolve here. I to the 4th, you could kind of create from previous values. It's really I squared times I squared. I squared being -1, so it's -1 times -1, which of course is just 1. Okay. And I to the 5th, just show you one more here and then I'll give you the pattern. You probably are seeing it already. I to the 5th could be seen as I to the 4th times I, right? It's if you add the 4 and the 1, you get 5. I to the 4th we already know is 1, so that's 1 times I, which is just I. And so the pattern, because you can always create the next power of I from previous powers of I, you're going to see this pattern continue, 1I, -1, -I, then 1I, -1, -I, and so forth. Okay? So this pattern continues, and it really is just these top 4 that are important. Okay? Every other power of I comes down to one of these 4 answers. Alright? So, how would you go about finding I to the, let's say, 11th power? Well, I to the 11th power is, if you take off a a power of 4 that's less than it, it's like I to the 8th times I to the 3rd. Well, I to the 8th, any 4th power is going to be, not 4th power, any multiple of 4 is going to be 1, right? I to the 4th is 1, I to the 8th is 1. So I to the 8th is 1, and I to the 3rd is -I, and so it's just -I. Anytime you get a power of power that's a multiple of 4, it's going to be equal to 1. And so those essentially are unnecessary, and we're just looking for the remaining power after you take off a multiple of 4. Well, a quick way to do that, instead of splitting up your powers, is just to divide the power by 4. If you divide the power by 4, 4 goes into 11 twice, and you end up with the remainder of 3. Well, the remainder is the one that matters. So whatever the remainder is when you divide it out is going to give you the answer. So if I wanted, for instance, I to the, let's go 31st power, well, I to the 31, well, 31 divide by 4, 4 goes into 31 7 times, with again a remainder of 3. So remainder of 3 means that we look at the I to the 3rd, that's just -I. Okay, so we can always look at the remainder on the division by 4 and then relate that remainder back to the original powers. Right? Okay, so that gives us our powers. I think I'll save the next topic for the next video.